Welcome back, everybody. In this lecture, we're going to introduce you to combination, what they are, and when to use them. Combinations represent the number of different ways we can pick certain elements of a set. Imagine you were trying to pick 3 people to represent your company on a very important technology-related conference. There are 10 people working in the office, so how many different combinations are there? If you calculated this as a variation, your answer would be 720. But you would be counting every group of 3 people several times over. This is because picking Alex, Sarah, and Dave to go to the conference is the same as picking Alex, Dave, and Sarah. As you just saw, variations don't take into account double counting elements. That is where combinations step in. This next sentence might sound confusing at first, so please pay close attention. We can say that all the different permutations of a single combination are different variations. Let us look at the Sarah, Alex, and Dave example. Choosing those 3 to represent the company is a single combination. Since the order in which we pick them is not relevant, choosing Sarah, Alex, and Dave is exactly the same as choosing Sarah, Dave, and Alex. Dave, Sarah, and Alex. Dave, Alex, and Sarah. Alex, Dave, and Sarah. Or Alex, Sarah, and Dave. Any of the 6 permutations we wrote is a different variation, but not a different combination. That is what we meant when we said that combinations take into account double counting. Okay. Recall that the formula for calculating permutations of n many elements is simply n factorial. Since n is 3 in this case, there would be a total of 6 permutations for choosing Alex, Dave, and Sarah. Since variations count these 6 as separate, we are going to have 6 variations for any combination. This means that we are going to end up with 6 times fewer combinations than variations. Using the formulas we already know, there are 10 times 9 times 8, or 720 variations. In terms of combinations, we have 720 divided by 6, or 120 ways of choosing who represents the company. Whew! Good job! Let's repeat the sentence we used before once again. We can say that all the different permutations of a single combination are different variations. There are 6 permutations, 120 combinations, and 720 variations. Hope it's much clearer now. Okay. From here, you can already imagine what the formula is. Let's construct it together. What's the number of combinations for choosing p many elements out of a sample space of n elements? As you saw in the last example, the number of combinations equals the number of variations over the number of permutations. Mathematically, we would write that as C equals V over P. If we plug in the formulas associated with variations and permutations, we get the following formula. N factorial over P factorial times n minus P factorial. Let's apply the formula to our example. The number of combinations equals 10 factorial over 3 factorial times 7 factorial. After simplifying, we get 8 times 9 times 10 over 1 times 2 times 3. This is equal to 720 over 6, which is 120. Exactly what we got earlier. Just to make sure everything is on the same page, let's go through another example. What if we had to choose 4 out of 10 people to go to the conference? According to the formula, we are going to have 10 factorial over 4 factorial times 6 factorial combinations of doing so. After some simplifications, this would equal 7 times 8 times 9 times 10 over 1 times 2 times 3 times 4. After computing the values, this equals 5,040 over 24, which is 210. Good job, everyone. In the next section, we are going to introduce an important property of combinations, symmetry. See you all there, and thanks for watching.